worries. I would like to start just by acknowledging the organizing committee for giving to me the opportunity to participate in this nice summer school and to have the opportunity to discuss science with all of you in this very nice place. So please clap your hands for the organization committee. I know that this is a huge work, so thank you. Today, I would like to talk about acoustic metamaterials for perfect absorption and wave diffusion. Now I'm in the Institute of Mathematics, Pure Mathematics and Applied Mathematics at the Polytechnic Universitat of Valencia. And in my past, I was a senior researcher in the acoustic laboratory of Le Mans University. So this is why my background in acoustics and audible acoustics. So I was feeling like a black sheep of the day because nobody was talking about acoustics. Well, yes, Matthias was talking a little bit about ultrasounds, but now I will talk about audible acoustics. So. Yes. So today I will talk by using this kind of structures. Basically, I will talk about waveguides with a Helmholtz resonator or point resonator loaded in parallel to the waveguide. And I will try to analyze what are the conditions to design perfect absorbers or good diffusers for waves, in that case, audible acoustic waves, but this can be generalized. In particular, I will talk about scalar waves. And when preparing this summer school, I was hesitating also to prepare a talk on correlated disorder and wave propagation in hyperuniform materials. So I have prepared. I will not give it. But if you want to discuss with me, I will be glad to discuss about this topic. So scalar waves in hyperuniform materials, and I will be glad to discuss and to show our results in hyperuniform and also crystalline structures. You can also work in acoustics with porous materials, and you can design very nice things with the new 3D printing techniques, and you can design very good absorbers using the techniques that we will discuss today. And you can, in fact, in all of that cases, basically you are working with the Helmholtz equation. But if you go to vibrations, in that case, you can work with biharmonic wave equations, biharmonic equations, or more complicated equations. So, but today I will stop with Helmholtz equations. So I will talk in that case, perfect absorption and metadiffusers using Helmholtz equation. Okay, so today I will start by a motivation of my work and why I want to discuss perfect absorbers and metadiffusers using audible acoustics. And then I will explain you two examples of deep subwavelength perfect absorptions, one working in reflection and the other one working in transmission using degenerate resonators in that case. And then I will talk about metadiffusers, and I will show you two examples, one metadiffusers based on slow sound systems and the other one using spiral sound diffusing metamaterial, because I saw that you used the picture in the summer school announcement, so I will try to explain how is it working. Okay, so in audible acoustics we have mainly two big problems. The first one is the absorption of waves, and the second one is the diffusion of waves. I think that most of you know the anechoic acoustic chambers. So in order to absorb energy, we need big systems of porous materials that are working in a broadband range of frequencies. But in fact, they are not so much efficient in terms of space. So we need big systems of porous materials in order to have broadband efficient absorber. Yes. In fact, it's a good question because it's not a scattering. Yes, you have a surface in which you send a wave, and then the surface is scattering the wave, but you are studying how this wave is distributed angularly. So it's like diffusion. Yeah, scattering in acoustics. we call diffusion because we call that diffusers, acoustic diffusers. But in reality, you're right, you can call it like a scattering. In fact, yeah. Okay, so in both cases, they are not efficient at low frequencies because mostly both of them, they are working at the lambda quarter resonance. So it's quite big if you want to go to the low frequencies. So the question that we address today is if we can find sub-wavelength structures based on resonant systems called metamaterials to improve the behavior of the existing systems for absorption and diffusion, and if we can control the absorption of sound efficiently at low frequencies by using metamaterials. These are the two questions that we want to address today. So we need several ingredients. The first one is that we need resonators in order to shift down the frequencies in audible regime. But we need to introduce either the slow sound concept or the coiling up systems. So imagine that you have here a quarter wavelength resonator. This is a quarter wavelength resonator, and the frequency, the resonant frequency of this quarter wavelength resonator is C over 4 times the length. So if you want to shift down the resonant frequency of that system, you have two options. The first one is, okay, let's do L big. So if you increase the length, then the frequency will be shifted to low frequencies, and this is what it has been done by calling up in the works of colleagues from Hong Kong, in particular Jensen Lee and collaborators. And the other option is, okay, you have sound velocity, so you can try to modify the structure of your resonator in order to reduce sound velocity inside the material to shift down the frequency. So you can do that by introducing resonators loaded in this waveguide. So, okay, if you introduce resonator in a waveguide, then automatically you can change the dispersion relation of the fluid, of the propagation in the fluid inside the medium, and in fact you are introducing immediately effects of slow sound here, and also the effect of losses that, in particular for audible acoustics, are not negligible, and this is why we need this kind of system in order to do absorbers. Okay, so we will mix these two properties in order to work to develop perfect absorbers and meta-diffusers. So, okay, these are the systems that we are developing. So basically we have a waveguide. In this waveguide, we load Helmholtz resonators that are working at a given resonant frequency, and the presence of these resonators will induce some properties in the medium that will produce some properties in the propagation of waves inside. So basically what we are doing is we will have this waveguide with Helmholtz resonator that will be either open in a transmission problem, I will call that the transmission problem, or we will put in the background, we will put a rigid end, so everything will be reflected. This configuration will be called the reflection problem. So in that systems, the losses are accounted by using the viscothermal losses. You can use the model of Stinson, and basically what we are doing is introducing effective parameters in the medium that we are using here that are frequency dependent and complex, and this will introduce the viscothermal losses, and basically it depends only on the geometry that we are using. So if you tune the geometry that you are using, you can tune the losses that you are introducing. Okay. We are also considering the the correction length of the Helmholtz resonator and the slits radiation in that system, because you have also that kind of effects. But this is really details of the mathematical modeling. I will try to do some toy models that I will show you later. So if we have a system in which we have Helmholtz resonator like that, periodically spaced, we can calculate the dispersion relation inside of this medium, considering that this is infinitely large in that direction. And you can compare this dispersion relation with that of the air, so with that without the Helmholtz resonator. So here, for example, in here you see a very small dotted line here. I don't know if everybody can see, but all of that, this dispersion relation is the dispersion relation of the air inside the waveguide without the Helmholtz resonator. If you introduce the Helmholtz resonators, then you have this dispersion relation in blue here, introducing a band gap, because I'm plotting the real part of the wave number in terms of frequency here. You have the resonant frequency of the Helmholtz resonator, and you can see that here you have the transmitted band, and here you have the band gap, okay? So if you analyze the slope of this dispersion relation, is very, very small with respect to that of the air. That means that the group velocity is very small with respect to the air. So by introducing the Helmholtz resonator in the waveguide, you can tune the sound velocity inside the structure. And if you, in fact, here in blue is the dispersion relation in the lossless case. I'm not considering any viscothermal losses. But I can calculate the dispersion relation by considering the viscothermal losses by using the Stinson model or toy model. I don't care. You can use a complex wave number and complex and frequency dependent properties in order to introduce that kind of losses. So here you have the band gap, and in fact, just before the band gap, this is the imaginary part of the wave number. In the case of the lossless case, you don't have imaginary part because you don't have losses. When you introduce losses, then you have the imaginary part here in the propagating band, and in fact, you can play with this close to the resonant frequency of the Helmholtz resonator in order to introduce effects of losses. But if you go to this regime, you can see that in this regime, the real part has some value, so you have a slow wave because the slope is very small with respect to that of the air, but the imaginary part is 0. So in this regime, I will have structures that will scattered wave with some properties dominated by the slow waves, and in region close to the resonant frequency, I will have scattering, but with a strong slow wave properties, but also with some effect of losses in the imaginary part. So I will have some attenuation that I can exploit to design that kind of systems, in particular absorbers. So if I work close to the resonant frequency, I will design absorbers. And if I'm working far away from the resonant frequencies, I will use this configuration to design meta-diffusers, or diffusers in general. Okay, here you have an animation in which you can see the effect of the slow sound. So basically, I'm plotting the wave propagation at a frequency over here. So you can see that outside the system, this is the phase. So you can see that it's traveling with a given velocity that corresponds to the velocity of air in free situation. And when it goes inside the waveguide, due to the presence of the Helmholtz resonators here, you have propagation with very small sound velocity. So you can see that it's stopped here. So if you try to analyze the resonant frequency of the complete system, this is like a Fabry-Perot resonator, but with a group velocity or sound velocity that is much smaller than in reality if you don't have the Helmholtz resonators. You can use that kind of systems in order to shift down the resonances. Okay, so these are the basics of the system that I'm used to design absorbers and diffusers, and now I will focus on the absorbers. So during my talk, I will talk always in the reciprocal scattering problem. Okay, so I can have symmetric or non-symmetric scattering depending on the symmetry of the resonator that I'm considering, but I will always be in the reciprocal regime. So in that case, I can use the very well-known nomenclature of the scattering matrix. So basically, I have a resonator, point resonator that is placed at a given position, in that case x0. So I have 2 waves that are ingoing to the resonator and 2 waves that are outgoing from the resonator. And I can relate the outgoing amplitudes with the ingoing amplitudes. And this is the scattering matrix, which is TT R minus R plus. Okay? T is the transmission coefficient, R minus and R plus are the reflection coefficient from both sides of the structure. This is the most general case in which the resonator sigma is not mirror symmetric. Okay? So basically, I will talk later with 3 problems. One in which I don't have the transmission. I will be in the reflection problem as I showed you previously. So in that case, basically, I will use, for example, that kind of problems. I have a quarter wavelength resonator that is plugged in the wall, like here in the roof. Okay? But these are not designed with the things that I will explain you here. Then, this case, the most general one, will be a waveguide in which I have 2 quarter wavelength resonators, for example, like that. So it's not mirror symmetric with respect to the center. So in that case, I will have transmission the same if I excite from the right or from the left, but reflection coefficient will be different in general. And the last problem will be this. So this is a symmetrical problem, mirror symmetric problem in the transmission. So I will talk about these 3 things. So, yes. Yes. If you are in a reciprocal problem, in fact, transmission will be the same from both sides, and reflection can be different from both sides. If you are in the lossless case, yes, no. First, in the lossless case, R plus and R minus can be different in phase. Amplitude is the same. Then if amplitude is the same, you have energy conservation anyway. So in that case, you have 1 reflection coefficient, you have 1 absorption coefficient. In that case, you have 3 scattering coefficients, R plus, R minus, and T. And because of that, you can have 2 absorption coefficients. Okay? But if you are in the lossless case, then this guy is 0, this guy is 0 in the lossless case. And then, in fact, what you have is that the modulus of R plus and modulus of R minus are the same, but not the phase. And in that case, just to finish discussion, you have R and T, and alpha is something like that. Okay? So, if you want to design here a system that absorbs the complete energy, what you need is to remove the outgoing waves. So to remove the outgoing waves, the only way to do that is to find the properties of the resonator in such a way that the eigenvalues of that scattering matrix will be 0. If the eigenvalues of this scattering matrix are 0, then C and D will be 0, and then you don't have nothing that is outgoing, and then you will create the perfect absorbers in that case. So in the case of the reflection problem, the scattering matrix is just the reflection coefficient. It collapses to an scalar. It's simple, and we will discuss this problem in details, or not in details, but more or less with some toy model afterwards. If you have an asymmetric resonator, again, you have this situation, and if you want that the eigenvalues will be 0, this should be accomplished. Okay? And we have done several works in order to create perfect absorbers by using this asymmetric resonator. The price that you have to pay here is that you have only perfect absorption from one direction, not from the other one. And then the symmetric resonator, I will discuss this in details also. This symmetric resonator, in fact, will need degenerate resonances. I will go into details on that. So I will discuss this and this. Okay, so imagine this case. This case is quite simple. If I call this the impedance at position 0, because this is x equals to 0, and this is the impedance of the medium, M. The reflection coefficient is Z0 minus Zm divided by Z0 plus Zm. And basically, if you want to have reflection equal to 0, you need to impedance match the condition, which is very well known. It's just, we are in a school, so I have to show the basics, right? So what are the conditions to have this system impedance match, or what I will call critically coupled? Okay, if now I'm using quarter wavelength resonators, the quarter wavelength resonator is rated with an impedance which is cotangent of KL. L is the length of my resonator here. And basically, the reflection coefficient can be written like that, where S2 is the section of the main waveguide, and the opposite. S1 is the section of the main waveguide, and S2 is the section of my Helmholtz, of my quarter wavelength resonator. So, okay, now let's analyze this expression in the lossless case. What you would expect in the lossless case? What do we expect? Reflection equal to 0.5. Reflection equal to 1. 4, I would expect in the lossless case, I would expect reflection equal to 1 for all frequencies being real. Okay? So if you analyze this reflection coefficient in the complex frequency plane, in fact, in the real axis, you have reflection equal to 1, which is a consequence of the conservation of energy, right? Then the mathematical solution to have reflection equal to 0 will correspond to a complex frequency, which is shown here. This is the 0, and in fact, you have a complex conjugate, which is the pole of this expression. And you have this 0 and the pole that are complex conjugated one to the other due to the time reversal symmetry. Okay. Now, what happens if I introduce the viscothermal losses? I will not introduce the Stinson modern viscothermal losses, which are very complicated. I will just introduce here a given admittance. And this admittance, I will say, okay, this admittance represents the viscothermal losses of my resonator. This is simple. If I do that, then I can obtain a reflection coefficient that has this expression, and around the resonant frequency of my resonator, I can expand, as in the previous case, I can expand the cotangent of KL will be pi over 2 minus KL, something like that. It's around pi over 2 because it's the resonance condition. And if I found if I look for the zeros and poles, in fact, what I have is that my pole and my 0 are exactly the same as in the case of the lossless case, of the lossless, right? But shifted down by the amount of losses that I'm introducing to my system, right? So, okay, the starting point is a situation like that in which the 0 and the pole are complex conjugate. So now, what does it mean to have impedance match system is that I have to introduce an amount of losses that will compensate this term here, S2 over S1, that corresponds to the leakage of the resonator. So in terms of critical coupling conditions, what I'm saying is that the losses that I'm introducing to the system are compensating the leakage of my resonator, and this produces this impedance match system. Okay, so by knowing this very simple toy model, you can then go to more complicated stuff. You introduce Helmholtz resonators, you introduce all the mathematical models, extinctions, length corrections, everything in your computer, and then you tune the losses in such a way that you compensate the leakage of the resonator, or you introduce the impedance match condition. And in fact, you can design this with an slit loaded with Helmholtz resonators. And what we have here is a peak of perfect absorption with a system that is lambda over 88 times. In fact, it's 88 times more than the wavelength that we are discussing. So you can see the difference with respect to the lambda quarter that I start my talk today. So it's huge, it's enormous. Here you can see it's the optimization procedure, and you can see how this is the zero of my complex frequency, of my reflection coefficient in the complex frequency plane. And you can see all the lines here are how the zero is moving by changing the geometry of my system. So basically, the losses depends on the geometry. And I can tune the geometry to have the zero exactly in the real frequency axis. Okay, so we have done similar stuff with more complex resonator. In that case, it was an slit with an aerogel here in the middle. And in that case, we obtain again the perfect absorption. But I'm mentioning this because you will say, okay, you are doing that in a complex frequency plane, and how can I work with complex frequencies? I cannot. I mean, experimentally, you measure and you have the real frequencies. So we develop this argon diagram. You can plot the reflection coefficient, the real and imaginary part of the reflection coefficient. Each point here corresponds to a frequency. So in the lossless case, what you have is a circle of unitary radius centered in the zero. As you introduce losses, this circle reduces the radius, and the center is shifted to the right. And the perfect absorption condition appears when the circle is completely tangent to the origin of coordinates. And this particular point corresponds to the configuration and frequency at which you have perfect absorption. If you have a circle that is smaller than that, that means that you have too much losses in the system, and you have to remove losses in the system. So this is a very good technique to know if from your starting point you can have a perfect absorber or not. If the starting point is like the red circle here, you cannot. You have to remove losses, and to remove losses is quite complicated. Okay, you will say, okay, this is working for a single frequency and for normal incidence. Yes, you are right, but if you study the dependence with the incident angle, you can see that as it is based in a resonant phenomena, is working up to more or less 60 degrees of incidence. And if you study the absorption coefficient in diffusion field, what you have is more than 95% of energy that is absorbed, which is very good. It's quite nice. Okay, so now you will say, but this is working for a single frequency. Okay, so now that you understand how it's working for a single frequency, because you have a Helmholtz resonator and then a slit, then you say, okay, I will put a second Helmholtz resonator, and I can do a cascade process in order to critically couple each frequency. And this is what we have done. So you can critically couple several Helmholtz resonator, and you will have the zeros of the eigenvalues of the scattering matrix in the real frequency axis, and you can push your system in order to compensate all the losses to have something that is flat. In that case, it's not perfect absorption, it's not one, but it's flat. So here, at each frequency, the absorption is 1, because it's designed to have perfect absorption. But in that case, you cannot have perfect absorption. It's very high, and you have something that is flat. Okay, so we have constructed this, and we have measured this in the impedance tube. You can see here the experiment in comparison with the finite element methods and also with the analytics. Here, the transfer matrix method. Here you have the reflection and the transmission, so you can see that this is working quite properly in terms of absorption. Okay, so now I would like to discuss a very nice collaboration that we have developed last years with Hong Kong University, with the group of Ping Sheng and colleagues from Le Havre, in order to design perfect absorbers for underwater acoustics. So when you go to underwater acoustics, things become more complicated because impedances of the materials are very close in general to that of water. So you can have some vibroacoustic coupling, and then you have to work to deal with that in order to see how you can design materials to be only excited by longitudinal movement and try it like a fluid. So this is what the colleagues from Hong Kong have done. In fact, they have created a composite material made of silicon rubber with a little bit of tungsten granule. And in fact, the thing is that they can change the impedance of the composite like a proportional number of the impedance of water. And the bulk modulus of the composite is the bulk modulus of water divided by the same proportionality constant. So in that way, the impedance of the composite, which is square root of rho composite B composite, is the same as the water. However, if you study the velocity, sorry, this is rho C, the velocity, which is rho C BC divided by rho C square root, okay? Then rho C B C water. But basically, I have written this here, so it's okay. No matters. So here you have rho alpha rho water. The bulk modulus is B over alpha, and then the composite is this. And in fact, what you are doing is you are trying, you can create the slow sound condition by dividing by alpha. So you can create the slow condition just by introducing this tungsten inside. So you can, again, start all the mathematical stuff with critical coupling and impedance match conditions. And basically what we have done is assembling of different quarter wavelength resonators. Here we have 9 Helmholtz resonators. The resonant frequency of that are arranged logarithmically in the range of frequencies. And basically what you can see here is that from 4 kilohertz, more or less, in water, the system is completely impedance match, and the absorption is pretty much high in a huge range of frequencies for underwater acoustics. Here again, you can see the similar rainbow effects, but in parallel. Okay, so we have checked that experimentally in the facilities of our colleagues in Le Havre, and we have observed a quite good agreement between the numerics and the experiments here. So numerics is the dashed line, and experiments are the dots here. So we obtain experimentally something like 90% of absorption from 4 kilohertz, which corresponds to lambda over 42. So it's quite big for underwater acoustics, and we are quite happy with the results. This is why I wanted to show you today. Okay, so now All the previous discussion was concerning this situation, basically, so in which you are working in the reflection problem. And now I want to work in the transmission problem, so considering also the transmitted waves. I will avoid this part because I don't have too much time. So I will discuss the mirror symmetric stuff. Okay, so in that case, in the mirror symmetric, the scattering matrix is TTRR, because as we have discussed, these are the scattering properties here. The eigenvalues of the scattering matrix are T plus minus R. Okay? So let's think a little bit on the scattering problem here. So you have something here which is mirror symmetric, and then I have a incident plane wave from the left, from your left. Then I have the reflected wave and the transmitted wave. Okay? So now let's try to think what's happening if in the mirror symmetric plane I put a Newman boundary condition or a Dirichlet boundary condition. Okay, so if I put a Newman boundary condition, this red line works like a mirror for the acoustic waves. So if I have this incident wave here, the mirror symmetric is exponential minus ikx. So what I'm having here is the reflected wave of this incident wave plus the transmitted coming from here. So in this symmetric scattering problem, my reflection coefficient of this symmetric problem corresponds to the addition of the two scattering parameters of my original problem. Now, if I do the same but with a Dirichlet boundary condition, the reflection coefficient here is the subtraction of the transmission and the reflection coefficient of the original problem. So look, what I'm having here is that this reflection coefficient corresponds to one of my eigenvalues of the scattering matrix. And the other one corresponds to the other. So if I want to have perfect absorption, I need to have both of them equal to 0. In fact, I have a symmetric problem, which reflection coefficient Rs is one of the eigenvalues here, and I can define absorption coefficient for this symmetric problem, and an antisymmetric problem where the reflection coefficient is the subtraction of these two, what could be R minus T, okay? So I have this absorption coefficient for this antisymmetric problem. So basically, what I have is that the reflection coefficient of my original problem corresponds to the average of the reflection coefficients of my two problems. The transmission coefficient corresponds to Rs minus Ra divided by 2, and the absorption coefficient is the average of the absorption coefficient of the symmetric and antisymmetric problem. What does it mean? It means that if I have these kind of problems, first of all, okay, what is a symmetric problem and what is an antisymmetric problem? Okay, so I will not do this. Okay, so let us consider Fabry-Perot resonance, resonator, like. First mode will be something like that, right? And second mode will be something like that, right? So first mode corresponds to a symmetric problem, because if I put a mirror here, I can reproduce the result. Second mode, if I put a mirror, I cannot reproduce the result. It's an antisymmetric problem, so I have to put a Dirichlet condition. So this means that for symmetric stuffs, or symmetric problems, I will excite symmetric modes. For the antisymmetric problems, I will excite antisymmetric modes, right? So what does it mean that in that kind of full problem, I have perfect absorption. That means that the absorption of the symmetric problem and the absorption of the antisymmetric problem must be equal to 1. That means that you need, at the same frequency, a symmetric resonance and then antisymmetric resonance. If you only have one of the two, and you critically coupled or you impedance match, you can only have half of the energy that will be absorbed. You need to have both kind of resonances in order to create that kind of perfect absorber. So, okay, how we can deal with that? So here I have my slit with a single resonator. If I study the transmission and reflection through that system, I will have a maximum of transmission here that will correspond to the Fabry-Perot resonance of that system that will be, in fact, dominated by the presence of the Helmholtz resonator. If I have two Helmholtz resonators, I will have one symmetric mode and one antisymmetric mode producing two systems. So what I have to do is I have to combine that kind of stuff with that kind of stuff and tune this and this in such a way that at the working frequency, I excite that mode and that one, right? Okay, so this is what I have done. It's very simple. Have waveguide, two Helmholtz resonator, one Helmholtz resonator. I consider the mirror symmetry just for a question of impedance tube measurements, but in fact, the simplest case is to consider that. Okay, so now, in this very simple problem, I start by imposing my Dirichlet boundary condition. I put my Dirichlet boundary condition, and I try to tune the antisymmetric waveguide, the losses, to have one of the eigenvalues of the reflection of the antisymmetric problem equal to 0. And this is what I have done here. I tune the geometry of that to have perfect absorption when I put this Dirichlet condition. If I put a Newman boundary condition, now I have to tune the symmetric stuff, the symmetric resonator, in order to have perfect absorption in the symmetric problem. And then what I have to do is, okay, I have to 3D print the geometry that I obtained by doing that process, put this slit inside of my impedance tube, and measure the scattering parameters. Okay, so this is what I have done. This is a picture from inside of my impedance tube. I have here the two slits. Inside, you can see the system with the two Helmholtz resonator and with a single Helmholtz resonator. And you can see that, in fact, at 800 Hertz, which is the design frequency, I have perfect absorption here in a transmission problem. So reflection and transmission are very small. Experimentally, we don't have perfect absorption because you can see here in the borders of my system, I always have some leakage that acoustic waves pass through. So it's very difficult to deal with leakage in acoustics, but we tried at least to obtain quite high perfect absorption. So basically, what you can see here is that at 800 Hertz, I can excite a symmetric mode and an antisymmetric mode at the same frequency. Both of them are critically coupled or impedance match, as you can see here with the argon diagrams of the two eigenvalues of the scattering matrices, and both of them are tangent to the origin of coordinates. And I have obtained perfect absorption in transmission problem by using these things which are called degenerate resonators, because I have two resonances at the same frequency. I have to say here that, in fact, the mathematical modeling of this system is a little bit more complicated than previously, because here we have to take into account the coupling between the slits, so we have to take into account the Bloch modes in the system, and I mean, the modeling is a little bit more complicated, but it's doable. Okay, so this is what I was saying. If you remove these Bloch waves, and you work only with transfer matrix or with plane waves, in fact, the system is not at all critically coupled, and this is not working because you have coupling between the slits. Okay, all of that can be found in in these references. There are 4 chapters and 1 article published in these 2 books, so you can check it later if you are interested, and if you want to discuss with me, no problem, I can provide you also some articles. Okay, so now to finish, I will go fast with meta diffusers. And in fact, what is a diffuser concerning the question of scattering or diffusion? So here you have a simulation. We have a wave front that is propagating through a structured surface. And the goal of a diffuser is to spread in all directions all the energies. And the goal of that is to avoid modes or specular reflections in acoustics that are not good, particularly in control rooms or in music halls or in practice rooms in which you need good acoustics and good, in fact, spread energy in all directions and avoid specular reflections. Okay, so what surfaces are good diffusers? Basically, the scattered wave in angular directions can be calculated by using the Fraunhofer Fourier approximation. And basically, the scattered field is the Fourier transform of the reflection coefficient profile. And a good surface or a good acoustic diffuser will be that has a flat spatial Fourier transform of the reflection coefficient of that surface. So you have to try to, you have to design a structure with a distribution of reflection coefficient in such a way that the Fourier transform will be as flat as possible. And in that case, you will have a very good diffuser in acoustics. Okay, so you can use, this is very well known since the works of Schroeder in 1975, where he discussed the design of this kind of phase grating diffusers in which they are working at the lambda quarter resonator, so they design a phase profile of the reflection coefficient in 1D or in 2D in such a way that the Fourier transform of that distribution is as flat as possible using some series that Schroeder discussed in his paper, quadratic residue diffusers or another kind of distribution. You can combine the phase of the reflection coefficient with absorbers, so you can combine reflection in the panel with absorption. So black here means absorption, and white means reflection. And in fact, in the white, you can tune the phase. And you can also add Helmholtz resonator. So the use of Helmholtz resonator in diffuser is very well known from 1998, so it's nothing new. But people from China use that kind of Helmholtz resonator in a new way and try to study how we can reduce the thickness of that kind of diffusers by using Helmholtz resonators. In fact, they obtain lambda over 8. And what we were thinking is, okay, now we know what are slow sound. So we can use this phenomena of a slow sound in order to shrink the size of the system and try to design diffuser with very small size. So it's lambda over 24 what we have designed. So basically, I will go fast here because I have already discussed this. I can design the Helmholtz resonator in each slit to have different slopes in the dispersion relation. This will give me different phase velocities, and this will give me different phases in the position of my resonator, of my diffuser, and I can design a phase profile that produce the same as we know from acoustics from the paper of Schroeder. So here, what I have done is this profile, and in this profile, I design a reflection coefficient that depends on frequency, and basically, the reflection coefficient is spread, produces a scattering that is very spread in directions, and basically, this is produced with 2 centimeters, so it's lambda over, I think is, we change from 27 centimeters to 2 centimeters of length. So we shrink quite a lot, that kind of things. So you can, just to finish, you can do the same with that kind of structures, okay? So you can create surfaces in such a way you control the phase, especially in order to create vortices in reflection. And in fact, here what we are doing is we create a vortex in reflection. In fact, the vortex is diverging, and as it is diverging, in fact, the acoustic diffusion is very good, because in fact, at the middle you have 0, you have a null, and here you have the incident wave and the scattered wave theory and experiment, and you can see that at the design frequency, the scattering produces this vortex. And in fact, if you measure the diffusion, the correlation scattering coefficient that measure how many energy is going to all directions with respect to the specular one, so meaning that 0 corresponds to a specular reflection, and 1 is energy going to all directions except the specular one. So you can see that from the design frequency, 2000 hertz, 2000 hertz at high frequency is very high. Okay, so I will stop here. I will have to thank the projects that found me recently to do research, and thank you very much for your attention.